Alrighty, y'all. Today we're taking a look at the second half of our Physics 211 homework number 1. And where we left off, we were just about to start question 3. So we have a bucket sliding off a ledge at 30 seconds, and we hear it clatter at the bottom of a well at 44 seconds. All right, so just real quick while we're thinking about it, I'm going to do 44 minus 30. And that's going to tell me that my total time elapsed while the bucket is falling, 14 seconds. So that's just something we're going to keep track of. And we're also assuming that Middle Earth has the same gravity as Earth, which is very convenient. Right? Same gravity means that G has a magnitude of 9.8 meters per second squared, which is pretty convenient. Ignoring air resistance and the travel time of sound, we want to find out how deep is the well. So we went through the procedure very step by step for the last couple of problems. So I'm going to start moving through it a little bit quicker now that we know what we're doing. All right, so for a kinematics problem, the first thing I want to do is draw a picture of what's going on. So I'm going to draw my well. All right. There's the bottom of the well, and there's the top. All right. So the next thing, once I have my picture, a beautiful picture of a well, I have to set where 0 is going to be. So I'm going to say that 0 is there, and then I have to set my coordinates. So I'm going to say that up is positive. All right. Now that I have all of my coordinates and all that stuff figured out, now I'm going to figure out what variables do I know and what do I not know. All right. So I have my initial position, I have my position at a time t, my initial velocity, I have my velocity at time t, I have my acceleration, and I have time. Right? So I want to figure out in this problem, what do I know, what do I not know, and what am I trying to solve for? Right? So the question is, how deep is the well? So how deep is the well? That would be this height here. So in the way that I have set up my coordinate system, since I set 0 at the top, right, and the bucket starts at the top, well, there's my first known value that I know my initial position is at 0. And I know that my initial position is at 0 because I set my 0 at my initial position. And I know that after some time t, the bucket will hit the ground and will be at a new position. I know that the difference between 0 and that position will be my x of t. So that tells me that is what I am solving for. If I can find x of t, then that's going to give me the height of the well. Right? Now I want to think about what else do I know about my situation. So I've managed to find what I'm solving for and a little bit more information, but there's a lot more variables to parse through. So we're told that the bucket slides off the ledge, right? So from that, I can assume that my initial velocity is 0, right? It's sliding off the ledge. It's not being like tossed up in the air, and it's not being thrown down into it. It's just kind of sliding off and accelerating downwards. So my initial velocity is 0 meters per second. My final velocity, well, we don't see the bucket hit the ground, so we don't really know what my final velocity is, and it doesn't really relate to what we're solving for, so I'm just going to kind of ignore that one for right now. We do know that my acceleration, right, because the bucket is in free fall, my acceleration is just the acceleration from gravity, and since we were told that Middle Earth has the same gravity as Earth, I know that my acceleration will be 9.8 meters per second squared. However, I forgot a very important part. Because I said that up was positive in my coordinate system, and gravity I know is down, my acceleration should be negative. And finally, I have time, which I solved for up here. All right, the time duration of my problem was 14 seconds. All right, so I have a lot of variables, and we have a few different kinematic equations we could use. So I'm going to write down both of them. X of t is x naught plus v naught t plus 1/2 a t squared, and v of t is v naught plus a t. Now, we have a third one, but we just derived that one in recitation today, so I don't think we were supposed to use it on the homework that was also due today. So we'll just start with these two, right? So I know that I am trying to solve for x of t, and I know a bunch of things, and I don't care about v of t at all. So this one's pretty easy to eliminate this equation and just use this one. Right? Because I don't care about v of t, and I'm actively trying to solve for x of t. So what I'm going to do is I'm going to come over here. And fortunately, all my algebra is already done for me. The equation's solved for x of t. So all I have to do is plug in the rest of my numbers and see what shakes out. So my initial position was 0. So rewriting it all, x of t is 0 plus my initial velocity was also 0. My time was 14 seconds plus 1/2. My acceleration was negative 9.8. And my time, again, was 14, and I got to remember to square it. All right, so these terms are both 0. Makes my life a lot easier that when I rewrite all of this, right, this negative in front of the 9.8, I'm just going to pull it out in front. Minus 1/2, 9.8. It's 14 squared. Punching that bad Larry into a calculator. It's going to give us negative 961.38 meters. Okay. And we can check that real quick with our units as well, because my acceleration is in meters per second squared. Right? I wrote that over here, my meters per second squared. And my time is in seconds, and my time is squared. So if I have meters per second squared, and I'm multiplying by seconds squared, my seconds squared will cancel out and leave me with meters. Right? So my units make sense, but how about that negative sign? Right? First thing it asks after we finish our solution, we want to be interpreting our answer. Make sure it makes sense in the context of the problem. Did we encounter any minus signs? Yes, we did, right at the end. What is the physical meaning? Well, the physical meaning says that my position, right, I said that down here was my x of t, my position after some time t, it's in the negative direction. Because I said up was positive and I had a negative acceleration, I kept all my signs consistent with my coordinate system. So this negative sign over here tells me that I have a position that is in the negative direction from 0. So if I'm asked for the depth of the well, a well won't have a negative depth. So if I'm asked for the depth of the well, that's supposed to be an equal sign, I would just take the absolute value, 3.8, can't write today, and circle that, right? Because though the position is negative based on how I define my coordinate system, the depth itself should be reported as a positive number because, again, we're remembering the physical meaning of what's going on. And we also want to remember that whatever coordinate system I decided to pick, it would have worked out. So if I took my well drawing, pasted it here, and had I just flipped it and said that down is positive, right? Then my acceleration, instead of being negative 9.8, would have just been positive 9.8 meters per second squared. And that my final position, right, because up here, the negative sign of my acceleration was what caused my position to end up as negative in the end. So my final position, x of t, would have ended up being that positive 961.38 meters, right? And that would have just given us outright the depth of the well, because I now say down is positive, and since my x of t is down from 0, it's a positive number now, and that makes sense. Okay. So again, any coordinate system I chose would have worked. I also could have set 0 down there if I really wanted to. Okay. The important part in these kinematics problems is to set your 0, set your coordinate system, and keep them consistent through the problem, and then everything will work out no matter what coordinate system you choose. Sometimes there are some coordinate systems that make things easier than others, but we haven't run into that case just yet. Any coordinate system you want to pick is perfectly great. Right? So, moving right along, question 4. Wow, isn't it so convenient that I already have all of these graphs set up for me? Because we're going to be doing some graphing for this one. I have a bicyclist. Starts from stop, accelerates at 1 meter per second squared for 6 seconds, travels at a constant velocity for 4 seconds, and then applies the brakes, decelerating at 2 meters per second squared until we come to stop again. All right, so we're going to be making an acceleration versus time and a velocity versus time graph. When it says be precise, that means we're going to have to be doing some calculations to actually figure out the values at different times on the plot. All right. So my handy dandy little picture here. Now I decided this ahead of time that I was going to say that the bike moving forward is in the positive direction. But again, you can say that the bike moving backwards is in the positive direction. Doesn't matter as long as you keep it consistent. And in this one, just in my brain, it makes sense to say positive is forward. All right. So if we're making our acceleration versus time and velocity versus time, whenever I'm graphing, I like to start with acceleration because usually that's the easiest because it's constant or just constant at different chunks of time. So I'm going to grab red so we can see it on my graph. But the first thing the bicyclist does, all right, from rest, then they accelerate at 1 meter per second squared for 6 seconds. So I say my acceleration for the first 6 seconds is 1 meter per second squared. Right? Now that's an easy thing to forget. Clearly I forget it sometimes as well, but just making sure that it's meters per second squared for acceleration and meters per second for velocity. Right? And again, I already have my time divided out for me. So 6 seconds is my first 6 seconds at positive 1 meter per second because it's going forwards and I know that my velocity is increasing in that direction. So if I'm starting with a 0 velocity and increasing in the positive direction, that will be a positive acceleration. Then I'm told that we're traveling at a constant velocity for 4 seconds. Constant velocity, that's something that I should be recognizing, that a constant velocity means the velocity isn't changing. So that tells me that my acceleration equals 0. All right, that's an important thing to keep in mind because that will keep coming back. All right, so for the next 4 seconds, which are also handy dandy marked off for me from 6 to 10 seconds, my acceleration is 0. I'm just going to put little points on the ends of my graph. All right, my acceleration is 0. Then, lastly, I decelerate at 2 meters per second squared until we come to rest again. Now, I don't know how long it's going to take the bicyclist to come to rest because I haven't done the rest of the problem. I don't know when the velocity is going to come back to rest. So for right now, I'm just going to draw an acceleration, just kind of leave an open-ended line. And because we said that when I have that positive velocity, accelerating was a positive acceleration, right? That means with that still with a positive velocity, decelerating, right, or slowing down means that's going to be a negative acceleration in this case. So I'm going to have negative 2 meters per second squared, and I'm going to extend that out just kind of all the way through to the end, and I'll trim it off once I know how long. Once I know when the problem actually stops, then I'll trim it off somewhere in there. Right? So there's my acceleration versus time graph. Again, since it's just a bunch of horizontal lines, I always like to start with acceleration because it's the easiest, right? But now we get to move on to our velocity versus time. So we're given some information. We're told that the bicyclist starts from stop, right? That means we're starting from rest, which means at time 0, our velocity is 0. Then we accelerate for 6 seconds, right? We saw that. So during this chunk of time here, right, during that first 6 seconds, the slope of my velocity graph, right, or my acceleration is the slope of my velocity graph, and the slope of my velocity graph is positive 1, right? So that means every 1 second, my velocity graph increases by 1. So 2 seconds, it increases by 2. Now, my scale is a little wonky here, right? I have 1, 2, 3, and I have 2, 4, 6. So just trust me that my slope is 1, right? When I draw it like that. And we can check our work, all right? Because I can see that after 6 seconds, my velocity is 6 meters per second. So let's check that real quick to make sure we're on the right track. So I know that my initial velocity is 0. And I know that, say, my velocity at time 6, well, I'm just going to write out my kinematic equation to start off with. V0 plus AT. So I'm looking for my velocity after 6 seconds of traveling at 1 meter per second. My initial velocity was 0. My acceleration is positive 1. And my time traveling is 6 seconds. So again, I'll have meters per second squared times seconds. So this time only one of those seconds cancels out, leaves me with meters per second, which is excellent because that's a unit of velocity, which is what I'm looking for. So my velocity after 6 seconds, 6 times 1, 6 meters per second. All right, wonderful. That is exactly where we ended up. So it makes sense with our kinematics and it makes sense with our graph. Right? Then, during my next chunk of time, my velocity, we're told that the velocity is constant, which means that the slope of my velocity graph is 0. So during that stretch of time, my velocity isn't going to change. All right, the slope of that line is going to be 0. All right, it's the same thing for when we have a constant acceleration and we just draw it as a horizontal line. Now I have a constant velocity that I'm drawing as a horizontal line. All right. So moving right along, now we need to figure out this last little chunk of time. So what this is going to tell us is how long it takes to slow back to a stop. So again, I'm going to write out my V of t is V0 plus AT. Right? But this time, we're not solving for my velocity given a known time. Now we're saying, okay, I know that my velocity will eventually get back down to 0. I want to figure out the time that it takes for that to happen. So I'm going to say that my final velocity is 0. My initial velocity for this stretch of time, my initial velocity for this chunk is 6 meters per second. And my acceleration is -2 meters per second squared. Okay. So when I solve this, I'm going to subtract 6 from both sides of my equation. So I'm going to have -6 equals -2t. Then I divide by -2 on both sides. Negative over a negative is going to become a positive. It's going to be +3. Now, the reason I had to kind of restart the problem and say my new initial velocity is here, right? Because remember, these kinematic equations only apply when I have a constant acceleration. And through this whole stretch of time, my acceleration changes. But if I only zoom in and only look at the first 6 seconds first, there I have a constant acceleration. If I look at these 4 seconds next, then I have a constant acceleration during that time. And same thing onward to here. So we call this piecewise constant acceleration. This is something you'll get a lot more practice with, but this is something pretty important to remember, that when I'm solving these, I want to solve for the end situation of one time chunk, and the end of one becomes the beginning of the next one. Right? So now my green time, I said, now it takes 3 seconds. And remember, this is 3 seconds after the beginning of the time chunk. So it'll get back down to 0 velocity at time equals 13 seconds. Okay. So that means I can come back up here, say, all right, once I hit 13 seconds, that's the end of my problem. I come back to rest, and I'm done. Done riding my bike for today. Right? Now, we need to figure out how far we travel in total. Unfortunately, we have some ways of doing this. Now, it kind of hints at part D that there's 2 different ways to do this. I'm going to do the geometric way first. So we know that the area under the velocity curve, right, so the area under all of these lines gives me my total displacement. Right, we talked about this in the last part 1, when we were looking at the area under that curve where my height was in meters per second and my base was in seconds. This is the same thing, except now we're just applying it to an actual situation. So if I get the area under each section of the graph and then add them all together, that will give me my total displacement from beginning to end, how far I travel while riding my bike. Right? So for area 1, right, that's a triangle. So it'll be 1/2 base times height. My base in this case is 6 seconds. My height is also 6, but meters per second instead. So it'll be 1/2 6, we'll say 6 meters per second times 6 seconds. Right? And in numbers, that means 1/2 6 squared, which will be 18 meters. Right? Because again, meters per second, and I multiply by seconds, so seconds cancels, leaves me with meters. Section 2, area 2, that one's going to be a rectangle, so I'm just multiplying base times height. So this was a base of 4 seconds, height of 6 meters per second. So there's A2 equals 6 seconds times, sorry, not 6 seconds, that was the first chunk. 4 seconds times 6 meters per second. And that's going to be 24 meters per second. Oh, not meters per second. Meters, right? Because meters per second, and then I multiply by seconds. Then area 3 is another triangle. Okay. So it'll be 1/2. My base is 3 seconds. We solved for that in our last chunk. And my height is 6 meters per second again. Right, so that one is 9 meters. Sorry, trying to remember how to do math there for a second. Right, so that means that my total area, or my total distance traveled, right? Total distance traveled after all of my time riding my bike, call that X final for this one, right, is my first area plus my second area plus my third area, which is 51 meters. Right? So during this whole stretch of time of speeding up, going at a constant speed, and then slowing back down again, I traveled 51 meters in total. Okay. Now we get to make our position versus time graph. It says, again, be precise, which means that we have to find our positions, wherever it may be, at a few different points, probably at the boundary points between the different chunks of time. We also have to be precise with the concavity or the shape, general shape of our graph. All right, for my friends who have taken calc, concavity is whether or not if it's concave up or down, it's a smiley face or a frowny face type shape, and that's given by our second derivative, or our acceleration. So we can see we'll have some positive concavity and some negative concavity. But for my friends who haven't taken calc, I'm going to work through this in a way that you don't need to have taken calc. So first thing we're going to do is we have to ground ourselves in some points that we know. So we know that my initial position, we said that starts at 0. Right? So I know my initial position, there's my x naught for the whole problem. And now we get to figure out our position after 6 seconds, after accelerating for 6 seconds. So we're going to use our handy dandy friend, our position kinematic equation. Writing while talking is not easy. And now, since we're solving for our position after 6 seconds, so x of 6, right? My position at time equals 6. My initial position, we just said that was 0. My initial velocity, we also know that's 0. Right? We said that up here at the beginning. The time that has passed, there's my 6 seconds, plus 1/2. My acceleration is 1, and my time is 6. I square it. Right? So x of 6 equals 1/2, and since I'm just multiplying by 1, I can just get rid of it. Multiplying by 1 doesn't change anything. And that's going to equal 18 meters. Now, the astute among us may notice that this is a little bit familiar. And in fact, it's the exact same math we did when we solved for A1. Right? My displacement during the first 6 seconds. There's my 1/2 6 squared. 1/2 6 squared. Right? It gives the same answer. So that's a fun and convenient coincidence, we'll call it for now. Right? So roughly at 6 seconds, so roughly 18 meters. I didn't give myself a nice scale that I could line up with, but we'll do our best. Because now we need to figure out where we are after 10 seconds. Right? So now our acceleration has changed, so we kind of have to reset our problem. So now my new kind of initial is at 6 seconds. So now I'm just zooming in and looking from 6 to 10 seconds what's going on. So what I have to do is I am now trying to solve for x of 4. Right? And the reason it's x of 4 is because, well, if this is my new 0, I go 1, 2, 3, 4 seconds. So after 4 seconds of traveling at my new acceleration is 0. Right? So now, having my x naught, now my initial position is where I left off from before, my 18 meters. My initial velocity, well, now I actually have a velocity, so at 6 seconds, my velocity was 6 meters per second. And my time, again, was at 4 seconds. And like I said, we're traveling at our new acceleration, which is 0. All right, so getting rid of that 0 term there because it's not useful. All right, that's going to be 18 plus 6 times 4. Now again, we can see that my second chunk of time, my displacement during my second chunk of time, is again the same exact equation that I used to solve for it before. Right? So if I finish out this, I can say, okay, this is going to be 18 plus 24. And my 18 plus 24, 42. All right. I'm just going to highlight that this piece is the same as A2. And from before, this piece is the same as A1, right? Just so we have it noted down. All right, so now I'm going to come back. I'm going to mark after, well, it says 4 seconds here, but remember, that's 4 seconds after I started my new acceleration. So my new acceleration started at 6, so 4 seconds after that is 10. So after 10 total seconds, I'm at 42. So we can mark that right about there. Right. Now we're almost done. Now I just need my total displacement after 13 seconds. And we already solved for it in the previous part of the question. But we're just going to do the kinematics just to show both ways of doing it. So again, now I'm resetting my problem. So my new 0 is after 10 seconds. So in total, I'm looking for my position after 3 more seconds. I'll call that x of 3. Right? My initial position is where I left off from before, my 42 meters at the end of that last chunk. Right? My initial velocity was 6 meters per second. My time is 3 seconds. And my acceleration is that new acceleration, that negative 2 meters per second squared. And again, my time is 3 seconds squared. Now, this doesn't quite look like our equation from before. And the reason is that it's just formatted a little bit differently. If we imagine this part, this 6 times 3, as a rectangle, right, with a base of 3 and a height of 6, right, if I have that big rectangle, and then I subtract the area of this triangle here, right, because now this triangle, well, instead of being 2 times 3 times 3, if we take one of those 3's with that 2, then I'll have negative 6 times 3, right, with that same 1/2. So there's the area of that remaining triangle up here. So I'm taking that big rectangle and subtracting this area because it's that negative slope that wasn't accounted for when I was just looking at the area. So it doesn't look exactly the same, but it's really similar, and we can see where our area and kinematics formulas, where they relate. So solving this for an actual number, my x of 3, again, is going to be 51 meters, exactly like we solved for it last time, because it'll be 42 plus 18 minus 9, right? Plus that rectangle minus the extra triangle. So I have my total displacement, again, solved for, of 51 meters. So I'm going to graph that right up here. It's right over 13 seconds, 51 meters. Let's try to find it. Keep it roughly to scale, and that looks good. All right. So now comes the hard part of connecting the dots on my position versus time graph. All right. So I want to start with the easiest section. So I'm going to pick the part with the constant velocity, right? Because my velocity is the slope of my position graph, a constant velocity tells me that this section has a constant slope, and the type of graph that we know has a constant slope is a line, right? So this has a constant and positive slope, which makes sense because during this stretch of time, my position is increasing, right? And I'm going to draw a line just like that, right? Then what gets trickier is these other sections because my velocity is changing. But it's not that bad when we break it into pieces. So initially my velocity is 0. Because my velocity is initially 0, right, my slope of my position graph is initially 0. So that means I have a horizontal tangent line at the beginning, which means that my position is going to kind of scoop out flat at first before starting to increase. And the way that I know that it's increasing, since my velocity, right, but the value of velocity at all of these times is a positive velocity, and also that velocity is increasing, right? It's getting bigger. So that tells me my position curve starts at 0 slope, then the slope will be positive and getting steeper as I get closer to that 6 meters per second. So the way I'm going to draw that, like that, right? So it's not super extreme, but we can see that right here, if I were to draw a tangent line, so if I just followed the curve, the shape of the curve right there, it would be a horizontal line. If I follow the shape of the curve right about there, it's a positive slope, but getting a little bit steeper. And as I go along, it gets steeper and steeper until it gets to the same steepness as this line here, right? Because again, my velocity doesn't change here. The way my velocity is changes, but the velocity itself at the end of section 1 is the same as the starting velocity of section 2. So the slope of this curve at that little break shouldn't change. It should be the same slope on this side and on this side of that line. Okay. So now we have to do the same kind of thing for my third chunk. Now my horizontal tangent line, right, my velocity is 0 out here. So my horizontal tangent line is at the end of the curve now. And over here, right, my velocity is still positive, right? My position is still increasing the whole time, which makes sense because I'm going from a lower position to a higher position. My position's increasing the whole time because my velocity is positive, but the slope of my position curve, because my velocity is decreasing, the slope of my position curve has to be decreasing, which means it's going to be getting less and less steep until it gets to 0. So the way that's going to look, I follow it kind of like that. Right? Not perfect, but pretty good. Right? I can adjust it a little bit. And again, like I was saying before, I want to try to keep this slope the same, right? Because it's the same velocity before and after that break in time. Same velocity right here as right here. But then the difference is that this velocity is going to start getting shallower and shallower as we go until we get to that horizontal tangent line where my velocity reaches 0 again and the biker stops going. Right. So we have graphed all of our graphs, and we accidentally did part D before we even were supposed to. Right? The two possible approaches to figuring out the distance traveled, one of them involves the graphs, and one involves writing some equations. Our area approach, that's the one that involved the graphs, found the area under the curve, and our equations one, that was our kinematics. And we already talked about where a lot of the similarities come from in what we're looking at. All right, so moving right along, our final question, the iconic, the infamous Roadrunner problem. All right, so we have a car slamming on its brakes so that it does not hit our friend the Roadrunner. And like before, we have some variables that we have to figure out. All right, so my initial position, my x naught, my position at some time t, my velocity, my initial velocity, my velocity at some time t, my acceleration, and time. All right. So I've listed out all of my potential variables, but I still have to pick my coordinate system. So just because I want to, I'm going to say 0 is where the car begins. So the car's initial position is going to be 0 because of how I define my coordinates. Okay. And just to make my life nice and easy, I'm going to say that positive is going to the right, because that just makes sense in my head. Positive is going towards our Roadrunner. Okay. And what we're going to do, we're going to write our equation of motion, giving the car's position versus time. And we have to think about any minus signs. So I'm going to start with our general kinematics equation. Once again, e plus 1 half a t squared. Right? And we're going to be filling in some of the blanks with what we know about these different variables. So my position at time t, well, we know that the road runner is 30 meters away. So what we're going to say, right, so that would be at a position of 30. And if we're trying to find the time, eventually we're going to be finding the time that it takes for the car to get to where the road runner is. So that already tells me that I don't know what my time is. I'm going to be solving for it. Right, but my position at that time, because we're saying what time does it get to the road runner? Well, the position when it gets to the road runner, that's my 30 meters. Okay. We also have an initial velocity given. We know because it says initially. Okay. And that's our 110 kilometers per hour. Now we right away should recognize kilometers per hour isn't in base units. So I'm going to convert that to meters per second. So 1 kilometer, 1,000 meters. Kilometers cancels. And 1 hour, 3,600 seconds. Hours cancels, and then when I multiply through, I get 275 over 9 meters per second, or for those of us that don't like fractions, 30.556 meters per second. So now that we have our units all squared away for that, all right, we can move on. Do we know our final velocity? Do we know the velocity of the car when we're on top of the roadrunner, or on top of where the roadrunner once was, because it hops out of the way? No birds were harmed in the making of this physics problem. All right. Do we know that velocity? Well, we know that we're slowing down. All right, where is it? Yeah, we're decelerating, but we haven't gotten to zero velocity yet. So it has to be some positive velocity that isn't zero. We don't know what that is. And also, it doesn't really help us to solve for it because we're just going to be solving for our time. So our last piece of the puzzle, because we don't care about that velocity, our last piece of the puzzle is our acceleration. So we have 9 meters per second squared as our magnitude of the acceleration. But we have to think carefully about our positives and negatives. So I know the velocity of the car is initially going to the right, and I know that it's slowing down. Because I have a positive velocity that is decreasing in magnitude, that tells me that my acceleration is going in the opposite direction as my velocity, which means my acceleration has to be negative. Right? So we should be associating, kind of like I was talking about before, we should associate decelerating with an acceleration that is opposite the direction of the velocity. It does not mean the acceleration is negative. It means that the acceleration is opposite sign to the velocity. Right. So now that we have all of our pieces together, we can sketch a graph of the car's position versus time. Now, I find it a little bit easier if I start by sketching the roadrunner's position, which is just at 30 meters and staying constant until it moves out of the way. And we'll say when it moves out of the way, it just moves off to the side, so it's still 30 meters from where the car started. Okay. But I'll find it easier to graph once I have some points to figure out what I'm graphing, right? So instead of sketching the graph first, I'm going to figure out how long it takes the car to get to the Roadrunner, because that's going to make our graphing a little bit easier to have some points to work with. So again, I already wrote my kinematic equation. I can just pull it down from up here. I'm just going to be plugging in some numbers and solving for time. All right, so my position is 30 meters. My initial position was 0 meters. My initial velocity, that was that 30.6 meters per second. Time is what we're solving for, plus 1/2. Then I have -9 for my acceleration, -9 meters per second squared. And I have t squared. Right. So I'm going to simplify this and move things around a little bit. So I'm going to first, because this term is negative, because of that negative sign there, I'm going to add 1/2 times 9t squared to both sides of my equation. And what that's going to give me, it's going to give me, well, 1/2 9 over 2 t squared plus 30 equals 30.6 t, right, because I got rid of that on that side. And then I'm going to subtract 30.6 t from both sides of my equation and rewrite it. So it's going to be my 9 over 2 t squared minus 30.6 t plus 30 equals 0. Now this, we can see, is our a t squared plus bt plus c equals 0. Right? The difference from what we normally see for our quadratic equation is that these t's are usually x's, but it's the same exact thing. Now instead of writing x equals, I'm just going to write t equals negative b plus or minus square root b squared minus 4ac all over 2a. And again, I have to plug in each of my pieces. So b is negative 30.6. I don't know why I started with b, but that's fine. A is 9 over 2, and c is 30. So when I plug all of this in, I have to switch colors back. Negative b, negative 30.6, plus or minus the square root, negative 30.6 squared, minus 4 times a is 9 over 2, c is 30. I close my radical, and then I fraction, all divided by 2 times 9 over 2, 9 over 2. Right. Now, I could simplify this. I could do some mental math, or I could punch this into a calculator and forget the monstrosity that it is. So I'm going to do that second option. And because I have this plus or minus, right? One answer, I'll get plus for one of my answers, and minus will give me my other answer for t. So my two answers for time, 1.19057143063 seconds, and 5.59955. That looks like an S. They both look like S's. 5.5202616 seconds. All right. So I have my two values for time, and now what I can do, those are the times where the car is crossing that 30 meters mark. So I'm going to use those. So it's about 1.2 seconds the first time it crosses. So say that's about there. And it's about 5.6 seconds over here. And I know that the car starts at an initial position of 0. and it'll have to hit some kind of apex in the middle. We'll just guess that it's, it's going to be centered between the two of those, so it's right around there, we'll just say. And so just sketching a general graph of the car's motion. Sketch that like that. All right. Should be symmetrical. I'm not very good at drawing things, though. Okay. So, how long does the Roadrunner have to get out of the car's way? We solved for our 2 times where the car crosses where the Roadrunner is. But part D tells us that only one of those is physically meaningful. All right? So, in our physical problem, the car is decelerating, but it's only going to decelerate until it stops. The car is not going to continue with its negative acceleration after it's stopped, right? So once it stops, right, because here's where my tangent line is 0. After it stops, the car isn't going to start going backwards. It's not going to reverse back over the Roadrunner. In fact, it's going to, pick a color, it's going to just stay where it is. Right? Once it's stopped, it's going to just stay there. It's not going to reverse. It's not going to keep going. So that whole section might be mathematically what's going on with the equation, but we have to remember that we're representing a physical situation, and we have to remember physically what's going to happen once the car stops. Right? So that tells me that this is not the answer, right? That 5.59 seconds, that would be if the car continued to accelerate at that constant acceleration and backed over the Roadrunner. The reason that our model, our equation breaks down after we stop is because my acceleration is no longer constant. Once the car stops, the acceleration goes to 0 because the velocity is no longer changing, because the velocity stays at 0. So that's why this second one is after my acceleration has already changed and gone to something else, which means that my correct answer, where's my highlighter? There it is. My correct answer is my 1.19 or 1.2 seconds, you can say. And we can look at what's physically happening in our problem. I can see an initial position. I have a steep slope here, and it starts to get less and less steep when it hits the Roadrunner, or hits where the Roadrunner was. Sorry, the bird gets out of the way. Hits where the Roadrunner was the first time, and it continues until it stops, and then it stays stopped for the rest of the problem. So this is our real position versus time graph, instead of the one that loops all the way up and over. Okay. So as with any question, I want to make sure that when I'm circling an answer, I'm not just answering the math problem. Because the math problem of solve this quadratic equation has 2 answers. But our physics problem only has 1 answer, because there's only 1 answer that actually makes sense in the actual context of our problem. All right, so that's all I have for your homework, homework 1. I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain, and I'll do my best to try to explain it, because I guess Sydney explains stuff.